Hello, hello. Excuse me. That's a rough way to start. Hello, hello, hello. Good afternoon, Genesis. Awesome. Good afternoon. Excuse me. Oh my God. Um, oh my cork. Hold on a second. So, okay. There's Annie. There's Kaya. There's Vanita with a. Ooh, wait a minute. Wait a minute. Okay, I'm gonna distract myself, of course. Oh my God. Oh my God. Oh, I'm embarrassing myself. I can't remember. All right, I'll get back to that. I'll get back to Vanita, but well, anyway, all right. And good afternoon, Yaneli, and good afternoon, Chastity, and more people are coming. I'm all embarrassed now. And now the chat. Good afternoon, Yaneli for the double. Good afternoon, Gabriella for the double exclamation point. Awesome. Good afternoon, Vanita with the double. Good afternoon, Genesis with the double and with the early. Um, okay. And there's more. Sorry. Good afternoon, Kaya with the double. Good afternoon, Carlos. Good afternoon, Chastity with the double. Good afternoon, Ariana. Good afternoon, Natalie with the double. I feel like. No, I just made that up, but okay. Oh, good afternoon, Mariam. Good afternoon, Sydney with the Sydney. Oh, you're so weird. Okay, sorry. Inside voice. It's funny because I'm realizing why I think Sydney and Natalie because because they were on a video that I was just watching. Second, anyway, whatever, it doesn't matter. Yes, and good afternoon, direct chat person who is saying finally the midterm is over. That's some excitement there. Yes, and I'll address that in a minute, but I'm glad to see some enthusiasm about your accomplishment, which I will address. But yes, direct chat person. Okay. Well, apparently my dog is also enthusiastic about it. All right, hold on. So let's get Oh, Psyduck. That's what I'm trying to. But is that Psyduck? Can we see your dog? At some point you will. I mean, yeah, not at the moment because I'm already like attention deficit struggling. You will at some point. Um, yes. Am I right? Is that Psyduck? That is Psyduck. Okay. And which evolves from, oh my God, which evolves into Gold Duck. Gold Duck. Oh, it's been a while. Sorry, that Jen. Sorry. Um, Okay, very rabbit holey of me. Uh, okay. So let me look. All right. But so here we are. We're gonna do in a few minutes. Well, in a few minutes, we're going to like really move on in the material in the class and all of that. Let me just make some comments first. Sorry, and look at something. Hey, look at that. Wow. Okay. Yes, this is not a sidebar. This is not about a Pokemon or a dog Pokemon. Um, Now I am sidebarring. I love the dog Pokemons, but I'm like Growlithe. It's not about or Arcanine, not about Growlithe or Arcanine. Um, it is a moment of happiness that I'm authentically experiencing right in front of your very eyes about you. Yes, you, anybody who is here right now and hearing me, I'm very happy with you and for you and proud of you because every single one of you has is he every single one of you who is here has turned in your midterm on time and even if and even those of you who are not here right now, which I mean, I have to look at that in a moment because I will because it is a midterm. But just for the to be clear to those of you who are here, if you are noticing that a colleague of yours is not here right now because that was the expectation that they would be the day of midterm, I will at least tell you whoever is missing right now, and yes, and I'm seeing who's missing. Believe me, I'm aware. if certain people are not here right now, there are a couple people that made an arrangement with me that told me in advance that they had an issue. Okay. But you should also know, all of you who have done the double right thing by getting this midterm in time and being here, you should know that anybody who is not here did turn in their midterm on time. And I always give a little speech when the midterm comes in of congratulations and to like it's a direct like it's like whoo, like let's have a little moment of whoo. Um, but I want to say this may be unprecedented that this class has 100% return rate. And I mean, not even like sometimes I'll say that in classes, like that every single person either turned in the midterm or made a special arrangement with me, because of like understandable circumstances or something. So in other words, everybody's accounted for. Like sometimes that is true. But I just want to pause and say that in this class right now, it's more than just that you're all accounted for. It is that literally, well, I think, wait a minute, actually, I'm checking something specific. Wait. Well, there's one. Oh, no. Yes. Literally every single one of your exams is totally 100% in and in on time. So, and that is really something, guys. Like I'm clapping. I don't know how you would clap for yourself, but like you should know that I think that that is meaningful. That's hard to happen. And some of you have, had me before, like, please forgive me. I'm going to give like a little quick speech here. Like, it's very important to me that you realize that you should feel relieved and like we are going to do more physics in a couple of minutes. Like we have to move on with our lives. But before we move on with our life, and we're not going to talk about the exam, we're going to talk about like new physics. So in a way, in a couple of minutes, it's going to be sort of fresh start for some of you anyway, in terms of the material or in terms of your grade or whatever. But let me make very explicit. Um, Let me make very explicit that you deserve a moment of recognition that you just did something and you did it right. And I mean, on a big level, you did it right. And for some of you, for many of us, what you just did was not easy. Maybe it was easier than you thought it was going to be. Like maybe two questions was more manageable than you thought it was going to be three, or I don't know. Or maybe you secretly think the whole class is a joke. I don't know. That's between you and yourself. But I will say that I think physics is hard. I can't remember any physics exam I ever took that I thought was like a total joke or that was easier than drinking a beer or whatever. Like they take something out of me and I like physics, right? So I imagine that it took something out of some of you. Also, for some of you, if you think like taking it home and doing it under non-test conditions and having for some of you, that may even make it seem like so easy that you might have given yourself less time than you thought you needed. And then at the end, it becomes like a heart attack or who knows? Everybody has a different story. I'm just trying to say that I want you right now to recognize that I have not looked at the documents. Neither of us knows right now what the output or the outcome is going to be. So I think you deserve a moment where you can say to yourself, it doesn't matter what the outcome or the output is going to be. What you did was something real and something not easy, and you somehow got it in on time, which is something. Because you could have not. I mean that wouldn't be good, but like it could have not, right? Whatever, you know what I'm saying. So you deserve to have a moment where you're like, oh, I just did something, woo, and now like the ball's in his court. Okay, it's out of my hands now. I did what I needed to do, and and that was an accomplishment, regardless of later on what he says about any possible areas of improvement or whatever in the document. And I mean that. Like, I wish more people had done that for me along the way. Like, you've just done something. Right now, it is perfect. And I mean that. Right now, as far as the universe is concerned, your exam is perfect. And it really is because the whole class did it. I mean, so yes, at some point, will I grade it? And might there be imperfections or areas for improvement? Sure. And maybe will every single exam document be like a 95 or 100? Maybe not. We know all of this. And we'll cross that bridge when we come to it. Those of you who have had me, I hope, know by this point that even if when you get the exam back, even if the number on the exam is like lower than what you want, or lower than what you're used to, or lower than what you want, basically, that's still whatever number you get on this document is not the grade that you're going to get for the whole course. I hope some of you have gotten used to the fact by now that in the end of the day, what you'll do for the whole course is still quite possibly very high. Um, and for many of us now, the exam's like a checkpoint. It's now like a second chance to do different material that we might be stronger at, to go back and still hand in old homeworks. The portals are not closed. You may get very little feedback on those old homeworks now, but you'll still get a lot of points. Or start looking for low-hanging fruit and seeing where you could start showing video or using your voice or things like that from here on in to grab as many more points as you can before the end of the semester. Like, there is still time for everybody to do well. Whether your personal standard is that you're still gunning for an A, or now you're trying to pass the course or whatever, I want to tell you right now, nobody's out of the game. Nobody is out of the game. And you should particularly feel that, given that you just turned this thing in and you've put the ball in my court now. And also on that, please bear with me. And especially if you did have me last semester, it will take me longer to get these back than I would like, longer than you would like. It will take me a while to get these back because I have a lot of them and they are long. I mean, obviously, you're one of many sections. That's the bad news. But the good news is, even last semester, by the skin of my teeth, I still got them back in time for you to get feedback and know what to do for the final exam. I didn't want to cut it that close, but we did accomplish that goal. This semester, I hope to not nearly cut it that close. You will get it back in time to know what to do better for your final exam. In fact, I'm going to make that my main focus in feedback. When I give you back this document, the main thing I'm just going to be looking for is, what can I tell this person that they need to do for their final exam? Okay, that now it won't be as fast as I would like. Like, I don't think you're getting these back next Monday. I just don't. Will I use a lot of my vacation, your vacation, to try to get through all of these and get it back to you by the end of your vacation? That's what I will try to do at your spring break. I will try to do that. That's not a blood oath, but that's what I'll try. But you'll have to bear with me and be patient and understand, tolerant, that the ball's in my court now and it will stay in my court for a little while. But all the more reason that during that time, assume you are doing better in the course than you think. And I am really proud of you in particular in this section for how. Oh, funny. Okay, I'm looking at the chat. All right, I'll stop talking in a second. Oh, I don't know if you're asking me. Well, I don't know yet about which combos people did. Anyone? That's interesting. Was that not the well? I'll find out. But
No, I was trying to ask
the other people. Okay.
classmate.
Yeah.
I
Okay.
don't know how to do it without like putting in the public chat.
Yeah,
I'm sorry.
No, that's fine. That's fine. Yeah. No, and if people want to, I'm curious too. If people want, we're taking a couple minutes on this topic, and then we're moving on. So if people want to respond to Andy's, I mean, I'm curious if the combination of 2 and 3, in other words, the pendulum, right? The pendulum and the Doppler rather than the math and the yeah, right. From what I gathered from Mercedes, the combo of 2 and 3 would have, I'm assuming that was the less popular combination. Yes. Um, wait, 1 and 3? Hey, are you sure that's what you mean? I don't think that was a choice. I'll find that out later. Right. One.
Wait, can you repeat what is not a choice?
Well, no, not what you
Really
said.
scared right now.
No, you shouldn't be scared. Someone just, I mean, I don't want to call anybody else, but no, someone answered you and said that they did 1 and 3, which I don't think was a choice. But I don't want to scare that person either. But
But I thought it was a choice because you said to pick from 1 and 2 and like 3 or 4.
wait, did I? Oh, wait, did I? Oh, Gabriella, thank you. Oh, wait. Well, if I did, okay, whatever I said then is what goes. Is that what I? Oh, sorry. I'm confusing the two classes. Okay. Okay. I'm sorry. I'm scaring. I don't want to scare anybody. Why would I have done that? Oh, yeah. Oh, no, no, you're totally right. I'm sorry. I'm confusing because I also teach physics 203. Sorry, sorry. Yeah, 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 yeah. Oh my God, I'm scaring myself. If that's and whatever I meant to say, if that's what I said, then that's what I said. What did I say? Okay, hold on, hold on. Oh my God, oh my God. All right, all right, all right. I'm sure you're right. I'm sure you're right. You must choose one. Oh yeah, okay. In your class, yeah, 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 yeah. And when I say your class, the other class, I just mean whatever I told you, I told all the 204s. I promise it was the same. I just did something different in 203. I'm not sure even why I did something. I did something different in 203. So okay, okay, you're totally right. I'm sorry. I don't want to scare anybody. Okay, okay, okay. No, 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 Brian. Sorry, so sorry. No, Brian, you're fine. You're fine. You're fine. Um, and Gabriella, thank you for the clarification. You're correct. Oh my God, Brian, I'm so sorry. I'm losing my mind. Okay. No, do not take the zero. And you wouldn't be a zero anyway. Do not take the zero. Um, okay, yes, and thank you, Ariana. Yes, yes. Okay, okay. So backing up. Well, oh, so what was well, you can continue this dialogue for a second. So feel free to you all can weigh in on it. I mean, if it helps any of you, you can weigh in on Annie's question, like while I'm talking. That's fine. Although, it's also so sad. A part of me, I don't even know. It's like sad that we're finding this out. Not sad, but sad. Like, in my fantasy of all of this, you all would have been like in a hotel room, no, like in a dorm room or a room, a lab room, the like entire time of the exam, all doing it together, which sounds like I'm like, that sounds weird, but um I love picturing you guys actually working together on these things. So I'm like, oh, you're sad. All right.
No, like a conference, you mean like a scientific conference? Like we all fly to like Washington, D.C. and like have like a like rent a room in Congress and then we just like talk about physics the whole time. And you
Yeah.
just like like watch us debate over like wrong answers and stuff.
Yes. I mean, honestly, I mean, I'm laughing, and that's funny the way Annie just put it, but honestly, and this is the other thing, like the whole point of board, like, look, I don't get to do board meetings a lot anymore because they're generally done in lab, not lecture, and also like I'm online and blah blah blah. But like I know a lot of you hate board meetings. I understand that. And I even understand that a lot of the lab instructors have mixed feelings about board meetings or like they don't do them exactly the way I do or would or whatever. But just yes, I love board meetings when I can be there and I don't say anything. I just let it rip of the class when I do them. And yes, the thing that my fantasy is that people get together and figure out this physics. And okay, do I have time for a quick story on that? But yes, I know it's a fantasy at this point. It used to be more true before COVID, and of course, it's even more true if it's a residential college. I mean, which makes me sad about. I think that's other conversation. But the one thing that I'm saddest about for all you people in general is that you don't get to live together. I do really feel like that is too bad. I mean, obviously, some of you are older and have families and this and that. Like, I get that, but it is nice to be able to really access your colleagues at all crazy hours, um, and informally. Like, I couldn't have, let me put it this way. Half the reason I'm so sympathetic all the time with you people of how hard you work and how hard this major is, which I really believe is, and it's not because I think I'm stupid or something. Like, I think I'm a pretty smart guy, but like, I could never have gotten through my undergraduate physics major without other people. I never could have done it or graduate school. Like, I could not have done this alone. I mean, I hope you guys are not doing it alone in general, anyway, that's a whole other thing, but okay, well, fair enough. Freedom is all right, fair enough. I mean, all right, all right. So I want to move on, but you can keep talking about who did what questions or whatever. Um, um, but what I just really want to say is congratulations. And I mean that. Like, my one little cliche about that maybe I've mentioned before, but it's like my new thing in my mind is for you to have turned in this exam on time, which again takes more discipline than just an in-class exam, like where you just literally have no choice. Like you just have to walk out of the room at a certain moment, right? Like this is a little bit more on you to manage your own situation. And for you to turn it in on time and then show up to class, I just want to remind you of something I do know about that. you're in somewhere in between two ends of a spectrum. One end, some of you turning it on, turning it like rock the thing, feel you rock the thing, feel like it, whatever that you just either it wasn't that hard or you made it easier or you went to town and made it like some of you are like handed in something that you're proud of and maybe you even finished it like hours in advance. If that's the case, I'm proud of you and that's amazing. And I've sometimes had that feeling in my life, but not all the time. So kudos to you if you can get yourself to that place. Others of you, others of you, by the time you handed it in, were shaky. Now, this is more the experience I can relate to. That many of you are like, this isn't my finest work. I don't totally get this. I'm not totally proud of this. I'm not sure I really want him to see all of this. Or, but it's almost 3:05 or whatever. Okay, this isn't great, and I wish I had more time, or I wish, but okay, I just gotta put this thing to bed, and I've got to cut my losses, and I've just got to do the honorable, dignified thing of facing the music and turning in what I've got, and here you go on time. Now, if you're in that position, then I'm doubly proud of you. Well, I don't want to compare, but then I'm really proud of you for being able to do that. Like that is hard. Like and I think it's a secret to life. It's one of is being able to not let the perfect be the enemy of the good, if you know what I mean. Like to be able to just be like, I've just got to be done now. I've got to be on time. It's not going to be perfect. Maybe I could have done better, but this is what it is. And it's better to give what it is on time than to like spiral into some crazy place. Like I think that's hard for many of us, especially those of us who are achievers, which we all are. Otherwise, we wouldn't be in this program and have made it this far. So if you turned in something that you're not totally proud of, but you nonetheless cut it off and turned it in on time, then I'm proud of you. And I'm dead serious. Like, because I've been there, I'm always there. And it takes a lot to be of self reflection to be able to do that. So, either way, take a moment before you get the grade back, give me many moments before you get the grade back, and just believe me that I'm impressed, and you should be impressed with yourself, and you should also be relieved and relaxed. And the material that we're going to do now in the next few minutes of in the next 45 minutes or whatever 50 minutes um is new material. It's totally new. Like I say, you could consider it fresh start, but also it's new to this to what you've been doing, um but I think some of it you'll find old and familiar, so you don't have to like maybe you can maybe be a little bit relaxed while you take notes and listen to it. I mean, okay. Freedom is that. Okay, so wait, is there anything else? So just okay. So hello, where's the board? Where's the board? Okay. So what we are going to do now is let Skylar into the room. Okay. What and her exam was in, I promise. I'm just saying. In fact, I think she was here and got kicked out. But either way, um, really 100%. I've never had I really don't remember the time I've had 100% like this. So really, um, okay. The equation on the board is the equation that is the goal of today. I want to build to this equation as usual, but it will be one of the last things we say today. But just as background or whatever, this equation is called Coulomb, and you may recognize it, or you may recognize it may in a slightly different form. You may recognize it from chemistry. This is Coulomb's law for the electrostatic interaction, or Coulomb's law for electrostatic interaction. Coulomb's and Coulomb is Coulomb. Um, so it's Coulomb's law for the electrostatic force. Interaction is a word for force. So this is the equation that captures the electrostatic force that one bit of charge will exert on any other bit of charge, electrical charge, in the universe. And this is our new topic. This is, in a way, our last topic, but it has many subtopics. But our last topic for the semester is all things related to electricity. That means like electrical charge, electrical force, electrical current, most of all, perhaps electrical field, and then things related to that, such as a magnetic field and electromagnetic radiation. But are just like we did a bunch about oscillations last semester, and then it was building toward the centerpiece, which were waves. And the reason that waves were like the centerpiece of the previous material is that waves represent an unthingy motion, right? Like the whole intrigue and importance of waves, as far as I'm concerned, is that they are a type of motion that is real, scientifically analyzable, but immaterial, right? They are an important phenomenon in the material world, but they themselves are not material. Well, similarly, our centerpiece for where all this is heading now in the latter part of the semester, we want to get to another kind of unthingy thing, another abstract, immaterial entity of the world, and the key version of that is called fields. So where the ship is heading now is to the study of electrostatic fields. That's like our goal. Today, first, it starts with an understanding of electrostatic forces, okay, hence this equation. But in order to build up this equation and explain things about electrostatic forces, I want to back up first a little bit and talk about or remind you or present to you the basics of a different force called the universal gravitational force. Okay, I'm going to talk about well, yeah, I'm going to talk about gravity for a little bit here to make a context. Um, Again, just some there's a spoiler alert. Like the punchline is that the way to understand electricity, the way to understand the electrostatic interaction is that it's remarkably similar to, if not mathematically identical to, the gravitational interaction. And the belief is that we all have a slightly easier time. I mean, most of us tend to have a slightly easier time picturing or relating to the gravity that exists between masses than the electricity that exists between charges, simply because masses are visible in our macroscopic world. So gravity seems like more of a macroscopic phenomenon. So the idea is that whatever understanding we can either have or build up about gravity, we're going to carry over into our study of electricity. That's the idea. Now, the idea also is that some of you have seen some things about gravity before, but some of you have seen less. So I'm going to do a quick review or presentation sketch of how gravity works, starting right now. But that just also reminded me, someone in the other class reminded me, you have as far as homework, like, so now we're moving to new material, right? To the ending part of this class, of this course. I believe that there's two homeworks that seem to be due next Monday or next time. I believe there's a homework 5A and a 5B. I just want to clarify the reason that there's two due on the same day and the reason they're called A and B is that it's a choice. I'm not taking it back, and I'm not going to misread. It's a choice. It's optional, and of course, in some ways, all homework is optional. And you never get a zero for not doing it, but you just get points for doing it, et cetera, et cetera. Well, but that's even more true in this case for homework 5. I don't really suggest or expect that any of you is doing both 5A and 5B. Choose one. Um, and the reality is to know that either one that you choose, I'll tell you how to make that choice in a second. But either way, whether you do A or B, it's not homework that's going to be directly on it's good to do, it's good for the points, it's good for the education, but it won't be, we won't go over explicitly 5A or 5B, and it won't be like explicitly on the final exam. In that sense, it's like optional. It's like for enrichment or extra practice or supplemental points if you need them or want them at this point. How to make your choice there. And the reason I just thought of it is in terms of 5A and 5B. 5A is called tone. It's more about further implications about sound and with regard and about sound waves and things like that. 5A, I would highly recommend that you choose to do if there's any chance you're either going to go on and take the MCATs at some point or some standardized test like that. If you're going to take a standardized or like a GRE or something, if you're going to take a standardized test that has any physics in it at all, first of all, let me know and we should talk for a few minutes at some point at your convenience just to psychologically prepare you. Um, but if you're going to take a standardized test, of that kind that has physics on it, 5A will be good practice for you. Like you want to start getting used to what it's going to look like to get physics questions that you don't think you've directly practiced or studied, but that you could still figure out from all the stuff that we have learned. Like, okay, whatever, you could talk to me about it, but 5A is good practice if you're going to be in that situation. 5B is more directly material for this class. Again, it won't be on the final or something, but 5B is more practice and enrichment or depth study of gravity because if you're struggling with electricity at all, it's much easier to get the concepts straight in a gravitational context and then carry them over. Okay, so that's how you can make your choice of whether to do A or B for next week, or you could do neither. But okay, um, so I'm going to talk about gravity now. I'm going to talk about gravity. Newton's law of universal gravitation. Assume, so look at the yellow for a moment. Assume that you have two arbitrary point masses, two bits of mass somewhere in the universe, maybe two bits of mass in the lab, maybe two bits of mass in outer space. And they're both points, i.e., each one of them has like an infinitesimal volume. They're really, like an electron or something, right? But they each have some number of kilograms, like an electron. I'm just saying there are objects that exist, whatever. I'm not trying to confuse you. You have two really small pieces of mass that do weigh something, and they weigh different things. Like one of them's more dense than the other. So you have like a big point mass over here, like a heavy point mass over here, and a light point mass over there. And we call them M1 and M2. Okay. And assume that they're separated by a displacement R, called R with a vector symbol over it, because displacement is a vector. So R is a vector whose R is a vector that points, it's an arrow that you could draw from M1 all the way to M2. So its direction points from M1 to M2, like by convention. Okay, and its magnitude, its length is what we call distance, measured in meters. So let me remind you before I go any further, let me just remind you something about vectors that we had to talk about in the context of homework 2 that now will start mattering, like the math methods homework. Remember that any vector, like the vector R with the arrow over it, can be written. Well, remember, look up at the blue in the like over to the side, right before where it says assume. Look at that blue reminder there that we learned in an abstract context. That is a definition of what we call a unit vector, right? Like R with a hat on top with a caret that we call a hat. R hat is defined to be R vector divided by R length, right? It's like a strange, it seems strange at first, but the R hat is called a unit vector. It is a given vector divided by its own length. The purpose of it, remember, is that it becomes a vector whose length is necessarily one unit, but whose direction necessarily is the direction of the vector to which it corresponds, right? So the whole idea of the unit vector is, if you now go back to the blue, if you look at the blue thing that's written right under the yellow arrow where it says, where it's trying to say recall, but that does not look like, where it says, well, it still doesn't look, but it says recall, okay? The idea of the unit vector is that if you multiply both sides of the blue by R, it allows us to view a vector any vector as a simple product of a raw length that has no direction times a raw direction that has identity length, right? So okay, this is like a reminder technically, but now you're going to maybe start to see how the unit vector like helps us notationally because what we want to say with this unit vector notation, we it means that the way we can picture vectors, one useful way to picture vectors, when you write the vector r arrow, when you write it as r times r hat, right? What that's like trying to say to the brain is like say the vector is 5 miles pointing northeast. The way we think of it is we first picture a little arrow pointing northeast, but that's only 1 mile in length. We first picture a unit vector, r hat, a 1 mile vector pointing northeast. And then we say to ourselves, okay, now we're going to scale up. We're going to multiply that by 5. We're going to scale it up by a factor of 5. So we're going to stretch that arrow so it's now 5 units long. So in other words, the big R, 5 miles pointing northeast, we're thinking of as having been constructed but as 1 mile pointing to the northeast multiplied by 5, stretched by a factor of 5, scaled up by a factor of 5. And that's why we call raw numbers scalars. Because, okay, so we think of a vector as something that got constructed by stretching or shrinking a unit vector. Well, if that's how we think of vectors, then what Newton says is if you've got a point mass over here and a point mass over there, then this point mass, M1, will exert a force, will necessarily, automatically exert a force on that point mass, a force vector that can be constructed in the following way. First, picture the unit vector r hat, like the white thing above the yellow thing, the white line above the yellow line. Like, first picture the unit vector for r, the vector that has a distance of 1 meter, but that points from capital M1 to lowercase m1. So picture that unit vector, okay, and then scale it down by a certain amount and then flip it. And the certain amount I'm going to explain in a second. And the flip I'm going to explain in a second. But when you're done, once you start with a unit vector, you scale it down, and then you flip it. And what you'll have is the resulting force vector that represents what M1 automatically necessarily does to M2, as long as M1 and M2 are point masses. So I hope you're sort of with me so far. So we think of the force, the gravitational force vector as a vector that got constructed like any other vector. Started with a unit vector, in this case, a unit displacement vector, and then got scaled down by a certain amount, and a certain amount that appropriately then changed its units from meters to newtons, and then it got flipped, and the final result was a force vector of a certain length and a certain direction that represents how intensely M1 is interacting with M2. That's what I'm trying to say. Now, the question remains, what amount did we scale it down by? And the answer is given by this equation, which you recognize, many of you recognize. So Newton's saying, so just look, so I'm obviously going to break it down, but I want you to see the way I'm writing it is that the gravitational force, hold on, let me just read. This is if we're looking at it this way. What I'm explaining right now is the force that M1 exerts onto M2, which is why I drew an arrow from M1 to M2. And what this expression here says, it says, well, the force will be R hat scaled down by an amount gm1 m2 over r squared. Like, of course, I'm going to like elaborate on each one of those letters, but the first thing I want you to notice is that that entire thing in the parentheses all together makes one big number. And that big number, in effect, is the magnitude of the force vector that we're looking at. And the direction of it is r hat. Like r hat equals 1. It's not multiplying any extra number by any of those numbers. It's just saying what direction this force vector is going to point in. But all the stuff in the parentheses is the magnitude of it. Okay. Oh, sorry. Wait. Oh, wait. That's a really good question. Wait. Okay. Wait. Do I want to answer that right now, or do I want to? Wait. Great question about the R. Let me answer that in a second. Let me say one thing and remind me if I forget. Um, so all the stuff inside the parentheses, well, M1 is all the stuff inside the parentheses tells us that the magnitude of this resulting force is going to be directly proportional to how massive one mass is, also directly proportional to how massive the other one is. So the bigger either or both are, the stronger this force will be. And then inversely proportional, this is partly I want to now address Andy's question, inversely proportional to r squared, where I just want to clarify the r in the denominator, is it's not a different r, but it's not r with a vector symbol over it, and it's not r with a hat symbol over it. It's just r, meaning it is. Oh, well, it says down here at the bottom. Sorry. Well, it's the r that's in the denominator of the blue up there. It is the r that's clarified at the bottom of this page. In other words, that r in the denominator is just the magnitude of the r vector, i.e., the r that's in the denominator is a raw distance. So what I'm still am going to answer Andy's question, I think, but the first thing I want to say, the part that I think a lot of you know from either a prior course or high school or middle school is if I didn't care at all about directions, if I didn't care about vector technicalities, I would be saying that the magnitude of the gravitational force between any two objects in the universe, any two point masses, is directly proportional to the mass of each object and inversely proportional to the square of the distance between the two objects. Like that is what I'm saying on a basic level. The bigger the objects, the stronger they pull on each other, and the closer they are together, the more they pull on each other. And I'm saying, wait, and then the Andy thing. And I'm saying, then there's a constant of proportionality called capital G, which I'll analyze in a moment. But as far as Andy's question, and I am curious about this, on the one hand, what I'm saying is, if it seems like there's like a lot of like that we're fixated on R, if it seems like there's like a whole abundance of R's all over the place, I mean, yes, but only because it's all different features of the same R. Like, there's no way I could write this equation and have the letter in the denominator be one letter, but the letter under the hat be a different letter. They are most definitely meant to be the same letter. So the thing in the denominator is the raw distance without any concern of direction. And the thing with the hat is the direction without any reference to distance. And that allows us to multiply properly and still know the direction at the end. So on the one end, I mean, we're fixated because they have to be the same thing. But if Annie is asking, and I will check in on this a bit, if Annie's asking, why do we not use like a D for distance or like for displacement or X, that's a very fair question. And some people do use D. They do. But the reason ultimately physicists like to use R and will also in the electrical equation is because it's so frequently, it's so frequently the case that one mass is so much bigger than the other, or one charge is so much bigger than the other, that one mass ends up orbiting around the bigger one. Like, it's so frequently this ends up having such widespread application to orbits that we like to think of that distance between the two of them as, in effect, a radial distance, as a radius of some larger circle. And even when things aren't literally orbiting, it becomes very convenient in physics often to focus on a distance, to think of distances in particular kind of forces, to think of them as radial distances, even when nothing's moving, to think of them as radial distances because of the whole idea that all radii of a circle are always the same. So, like, to think of something as a radial distance kind of cements the idea that it doesn't, then in some sense, when you're thinking about the distance, it doesn't matter if it's going that way or going that way or that way, it's going to be the same number of meters. So I don't know if that, does that answer your
Yes, very sufficiently. Thank you.
very sufficiently? Okay, thank you. Okay. Okay. That I should put that on my gravestone. Here he lies. He answered very sufficient. Okay, all right. Uh here he lies. And yet he told the truth. Just kidding. Okay. All right. So the other thing to say here is what's the deal with the G? So the G is a constant of proportion, the big G. Now, this is not little g, as you know. Little g is like ends up being how all of this gets applied in the particular case of being near the surface of the earth. But what I'm trying to say, so it's not inconsistent. Anything you felt you understood about gravity from physics 203 is not to be thrown away. It's not inconsistent with any of this, but it's all special case. All the stuff you know about constant acceleration, free fall 9.8, that's all the special case of universal gravitation being applied to the surface of the earth. Now I'm saying universally, any one object, not just earth, the center of any mass will pull on any and every other mass anywhere in the universe, and it will pull with an amount that's directly proportional to each mass and inversely proportional to the distance between them. But that's proportionality. What's the exact equation? There's a constant of proportionality that gets put in there to make the numbers work out well, so that you have an exact equality. And the constant of proportionality is a universal constant, like capital G. It's known as the universal gravitational constant. You don't have to memorize it, but you have to understand a couple of things about it. One is, so it's 6.67 times 10 to the negative 11th. Like that is what is plugged in on every single gravitational equation for any context, including like building rockets to go to the moon in 1969. Like that's the number. You need to know that it's a very tiny number. It's 10 to the negative 11th. So first and foremost, I'm saying gravity is universal. Everything pulls on everything gravitationally, but all other things being equal, most things pull with a very tiny amount. They have to start having very, very large masses to start making any difference in the numbers. And that's why we tend to care about gravity mostly in astronomical contexts of like stars and planets and so forth. Because there are other forces in the world too, which we're going to study next, which are a lot stronger than this one. But the other thing to notice about it is that the units of the number G are at first might seem like very bizarre units. I mean, newtons times meter squared divided by kilograms squared. They might seem bizarre, but they're completely deliberate and sensible. If you look, the whole purpose of the units is that the meter squared in the numerator of the G. I mean, it says newtons meters squared. The meters squared are there to cancel out the meters squared in the denominator of the equation, and the kilograms squared are there to cancel out the kilograms in the numerator of the equation. And what you're left with is just newtons. So the whole purpose of G, it's an important number, but it's not a magic number. It's there to make the units work out. It's necessary only if we insist on, which we do, on consistency and continuing to measure force in SI units in newtons. Okay, and so if you were measuring in inches and feet and pounds, then the number would be a different number and would have different units to cancel those out. So it's just a constant of proportionality and it's universal. Okay, so now what I'm saying is, if you look at this equation, then the way to look at this equation is it's the construction of a vector, of a force vector. It's telling you direction and magnitude of the force with which M1 would, or the force that M1 would exert onto M2. And what it's saying is, to go back to the other picture, it's saying first, picture the unit vector, the white little arrow with the R caret on top of it. First, you picture the unit vector that points from M1 to M2. Then you scale that arrow down by a number of newtons meters. Well, you scale it down by like the mass of one times the mass of the other divided by the square of the distance between the two times the universal constant. You multiply all those numbers together, you get one big scaling factor, which is generally probably a very small scaling factor, and which converts all the, and so you multiply your R hat by that. And now you'll have an F vector, a force vector that's a really probably a small number and measured in newtons. And then you notice then there's a negative sign before the whole thing. So that negative sign says now flip your vector, right? Your vector started being in the same direction as, so the R hat says that the force vector must point along the axis that exists between M1 and M2. That's what the R hat is saying, like point along that line from M1 to M2. And then the negative sign is saying, well, now flip that. So that at the end of the day, your force vector that you get is this tiny arrow. And again, it's not always tiny. I mean, if these were planets and stars, it'd be big, but you get this arrow at the end of the day that's pointing in the other direction. And it's called F. It's called the gravitational force. And what does it mean that it's pointing in the other direction? Well, it means that if we're looking at and this negative sign's always there. It's using the unit vector in a very meaningful way. It's saying that if you're looking to know how M1 is interacting with M2, if you're looking to know how M1, pushes or pulls M2, then the answer is that M1 will exert a force that points in the direction of M1, not in the direction of M2, a force that points in the direction of M1, meaning, well, I guess it says down here at the bottom in yellow, meaning that M1 will reach out to M2 and pull it towards itself. The negative sign, when all of my talk is the point of this whole talk is, in a way, I'm hitting an ant with a sledgehammer. In a way, I'm telling you something you already knew, which is that gravity is always a pull, never a push. You knew that. But now I'm trying to show you how we capture that in the mathematical notation, how we ensure that's true. And we use this mathematical notation very deliberately and carefully because not all forces are pulls. Some forces, such as protons against protons, are pushes, right? So I want you to see it in advance that R hat means we look in the direction from M1 to M2, but then the negative sign means go back in the other direction. So at the end of the day, the force is pulling M2 toward M1 rather than pushing it away. It's pulling it in, and i.e., we call that attraction. So from here on in, on a force, if you ever are expressing force as a vector carefully, like these kind of forces, if you see a negative sign on it, it means it's an attractive force. Negative means attraction. And conversely, positive would mean repulsion, pushing away. So I hope that's clear, maybe. So that's the gravitational force, the universal gravitational force between two point masses. And obviously I'm saying all of this. Hopefully you think it's true. Well, I mean, I don't know if hopefully you understand what I'm saying. I think it's true what I'm saying. I think you've heard some of it before. I'm just trying to add notational details to it. And I'm trying to set you up to be able to compare electricity to it. What was I going to say? But well, a couple of comments then on it, on this gravitational force. And also, just for if you care, like this is Newton, right? This comes from Newton, and Newton lived from 1642 AD CE to 1727. So this work on gravity is like really like the 1690s, late 1690s, like right before 1700. Okay, if for what it's worth. So, comments on gravitation. First of all, the gravitational force, it is a force. Everything I'm describing here is a specific force, but it is a force like any other force in physics, like tension, like normal, like friction, like the elastic spring force. So, like all other forces, it is I want to remind you that what it means to be a force is to be an interaction between two objects. Specifically, I mean, to remind you, I mean, that means to be a push or a force is one object pushing or pulling another object. A force is never something that you have. A force is always something that you do to something else. Like always, all forces. It's an interaction between two objects. Second of all, like all forces, it's a vector. That's why I had to just like spend 25 minutes fixating on the details of the vector. It has magnitude, it has direction. We can and must be careful about both of those aspects. Third of all, or C, the gravitational force is a force like any other force in the Newtonian program. It obeys Newton's laws, specifically Newton's second law, Newton's third law, by which I mean, let's talk about the third law for a second. Like the third law is still true. So I'm going to tend to talk about what mass one does to mass two. And in fact, the only reason I'm even calling them M1 and M2 is just so that my brain like knows what it's focusing on. So when we focus on the force that M1 exerts on M2, we say GMM over R squared, and we do all the sum of the vector, and we say that M1 pulls M2 toward it. Okay, and that's all true. But that's just like what we're focusing on. The fact is, Newton's third law is still true, and multiplication is still commutative. So it doesn't matter if you multiply M1 by M2 or the other way around. Everything I'm saying about what M1 does to M2 necessarily M2 is also doing to M1. Like that, I just will focus on one thing at a time. But Newton's third law is absolutely applying here to gravity. So things pull on each other, they don't just pull in one direction. And similarly, Newton's second law. Everything I'm saying about gravity now is about this particular force. Like all forces, it is one of many contributions that can be plugged into the left side of F net equals ma. Remember, the law was F net equals ma. The sum of all forces produces acceleration. No individual force necessarily produces acceleration. They all contribute to acceleration. So this is no exception to that. This can go into the left side, and you used to, just in the special case of surface gravity, you do like, you do like mg plus n cosine theta, whatever, equals ma. Still true, even if you're in the outer space. Gravity is just a contribution to the net force that yields the acceleration of any object. So, on the one hand, I'm saying gravity is just a force like any other force, and I'm just giving you the mathematical breakdown of how strong it is. But on the other hand, unreadable handwriting part number two, what it says there, holy moly, what it says there is the gravitation, what it should say there is the gravitational force. Yes, it's just a force. The grav force is a force, but it actually happens to be what is known as a fundamental force. Now, not all forces are fundamental force. Tension is not a fundamental force. Friction is not a fundamental force, etc. Gravity, and in fact, no force that we've seen yet is a fundamental force besides gravity. What do I mean that it's fundamental? I mean that one object, one point mass does not have to be doing anything in particular to exert a gravitational force on another point mass. All the point mass has to do is exist as a point mass, and it'll automatically, as far as we understand the world, a point mass will automatically be pulling on any and every other point mass that exists in the world. It doesn't have to have any particular velocity. It could be sitting still or moving, whatever. It's going to do it, right? And even more to the point, to say that gravity is a fundamental force means that one point mass doesn't need to be touching another point mass. It doesn't need to be in any kind of material or thingy contact with the other object. Now, this is like very important and a little bit heady. Just to be clear, I'm saying that the sun, if it exists, automatically pulls on the earth if the earth exists. There can be empty space between the two of them, and somehow the sun will pull on the earth. Interesting. Or there could even be stuff in between them, like Mercury could be in the way, and Mercury can't block the pull. The pull doesn't seem to need any material mediation to exist, and the pull can't be blocked by any material interference to not exist. It just seems to happen. It's called action at a distance. Now, I'm not claiming that that makes sense. I mean, I'm going to talk a lot more about it. I'm not saying, duh, can't you understand exactly that that would be true? I'm not saying that at all. Quite the contrary. But I am saying that it is true, or that it seems to, that all the evidence seems to suggest that it's true. That for a point mass to exert a gravitational pull on another point mass, all the 2 point masses have to do is exist. They can be absolutely separated by empty space and they'll still pull on each other. And we call that action at a distance, which you could sort of read at the bottom of the board. We call that action at a distance. And and it's so important and so kind of weird or unexpected that we even try to remember the specificity of the action at a distance. We say, yeah, they can be at a far distance and still be pulling on each other. Now, it's not totally counterintuitive. Like the farther away they are, the less they'll pull on each other. So it's not like chaos. The farther away two objects are, the less they pull. This action at a distance, this fundamental force, seems to be a force that is inversely proportional to the square of the distance over which it's acting. So that's what the last bit of this board says, that yeah, it's action at a distance. And what is the relationship between the action and the distance? The relationship is that the force is in, like that symbol, that alpha symbol. I think you've used it in lab, I hope, or that means directly proportional to. So the force is directly proportional to 1 over r squared, i.e., it's inversely proportional to r squared. So that's my comments on gravity. Now, we've got 13 minutes. Let's segue now to electricity. So now we get to the mid 1800s, and there's this French, like, so Newton was British, and there's a Frenchman, Auguste de Coulomb, um, who discovers, I mean, he's not the only one, of course, like, there's never only one, but he gets the credit for discovering that if you have 2 point charges anywhere in the lab or anywhere in the world, they will interact with each other in a manner that is shockingly similar to the manner in which 2 point masses interact. If you have 2 point charges, and what do I mean by charge? I don't know exactly. I mean, what do I mean by mass? I don't know exactly. I mean, mass is I do know that it's easier to relate to mass than to charge, which is why we always talk about gravity first. But mass is just a fundamental property that objects in the world seem to have. Charge is another fundamental property that many objects seem to have. In the case of charge, as you know from chemistry, first of all, it seems to come in two varieties. I don't know why. And not that I don't mean to be glib either. It's not like I've never wondered about it. Of course, sometimes I spend my life wondering about it, but I don't have an easy answer for you. And I certainly know that I don't need to, that I can do all of this stuff, and that all this stuff was discovered without anybody exactly knowing why. So it's okay. But charge seems to come in two varieties, and seems to exist in these like small packets that you learn about in chemistry called like protons and electrons, right? So, uh, which by the way also have mass, but they specifically are objects that have charge. So if we have 2 point charges, if we have a bit of charge over here, and then separated from by a displacement r, we have a bit of charge over there. According to Coulomb's law, there is a force that this charge exerts on this charge. Hang on, I should do this. There's a charge, there's a force that Q1 will exert on Q2 that seems to obey the exact same mathematical form as gravity. And that's interesting, particularly if we realize that it's also fundamental like gravity. Like this is everything I just said about gravity is true of this. It's also just acts, it just happens. Just as long as you have a charge over here and you have a charge over there, doesn't matter if there's space between them, doesn't matter if there's matter between them, they will just automatically pull or push on each other through empty space at a distance. So this is another fundamental force like gravity, and like gravity has this unexpected character of inverse R squared dependency. There seems to be a connection between a force being fundamental or acting through a distance and it having an inverse R squared mathematical structure. Now, is that a total coincidence? No. Did they understand why? Did it seem like a coincidence at first? Yes. Well, not entirely. I mean, to be really truthful, when Coulomb developed it, Coulomb already had a suspicion that this was going to look somewhat like gravity for reasons that I will get into, and that will even further address Andy's question of like why we're fixated on R's rather than D's. There is actually a logic to this, to the universe, I believe. But we'll get there. Right now, I'm just saying, note the interesting correspondence that the two fundamental forces that we're learning about right now, both are fundamental in that they take place, they enact action at a distance, and they both have this inverse R squared structure. Now, let me get more to the details of this. So the structure is the same. The details are slightly different. Let's get into the details. First of all, the constant here, instead of a big G, we have a K. Oh, we have a K, but it's like the third K that we have in this class. So I usually put a subscript E, meaning this is the electric K or the electrostatic K, or what people will call the Coulomb constant. Okay, it's serving the same purpose as the big G. It's a constant of proportionality. It's a universal constant of proportionality. And among other things, it makes the units work out. Now it happens that this number is a much bigger number. So right from the get-go, like if there's no all other things equal, the electrostatic force is far stronger than the gravitational force. Let's be clear for a moment too. If you have two electrons separated by a distance of 10 meters, electrons are a perfect example of things that we do regard as point charges. I mean, they have a certain amount of charge, each of them negative charge, and they take up like no space. Like really, electrons are regarded as Euclidean points. They don't have volume, they don't have a radius, but they do have mass. I mean, that whole idea of a point particle is not just in our heads, apparently. So if you imagine two electrons, they are point charges, but electrons also have mass, or did I just say that? So they're also point masses. So if you have two electrons in the lab, that's an example of two objects that will automatically exert gravitational forces on each other. They will automatically pull toward each other. But they also exert electrostatic interaction on each other, and they're both negative, as we'll see them, as you know from chemistry. So they'll push on each other electrically while they pull on each other gravitationally. They will. And all other things being equal, the electric interaction is so much greater. You see, it's 10 to the ninth, and the other one is 10 to the negative 11th. And then their charges, well, we'll get into that in a minute. If you just took two electrons and did all the math, you'd find that the electrostatic repulsion is like 40 orders of magnitude greater than the gravitational attraction. And I mean 40 orders of magnitude. I don't mean 40 times. I mean 10 to the 40th. So it's like, so electricity is like really powerful compared to gravity, just as a side. So that's one thing to notice about the number K sub E, but also notice the units are, again, meant to cancel out the units and leave us with newtons. However, in order to do that this time, it's not newtons meters squared over kilograms squared, it's over coulombs squared, because coulombs are the fundamental or are the SI unit of electrical charge. What the heck is a coulomb? Well, it's just that. It's the SI unit of charge. But to get a sense of scale or intuition, this is the last page of, yeah. And we have 6 minutes. Okay, perfect. just to get a sense, I'm not saying you have to memorize these numbers, but this is like a to give you perspective. And again, you've probably seen some of this in chemistry, but the charge of a proton, the charge of one proton is approximately positive 1.60 times 10 to the negative 19th coulombs. In other words, very small amount. In other words, a coulomb is a large amount of charge. We discovered it I mean, we discovered electrons after we discovered charge. So it's like all benefit of hindsight. It's like, it's inconvenient, but it's the case. Um, what is convenient is that an electron has the exact same amount of charge as a proton, only negative. Negative 1.60 times 10 to the negative 19 coulombs. And then for perspective, the mass, so they're the same. Protons and electrons have the same charge. Now they have different masses. An electron is like, 1,000 times smaller than a proton. Those are their masses right there. That's just for perspective, okay? Um, but then two quick things I want to say. One is I want to introduce one other number to you. You don't have to memorize it, but you need to know how it works. This number is called this E naught. It's called the permittivity of free space. Or we read it as epsilon naught. That number is 8.85 times 10 to the negative 12th Coulomb squared over Newton meter squared. Notice it's a very small number whose units are like the inverse of the K number. The reason I need you to know this number or know about it is that it turns out, just like R is more convenient to use than D, because it turns out that a lot of times we're thinking about these things like as radii, it turns out to be much more convenient to write that K number as a combination of other numbers. Like it functions, that constant, that Coulomb constant functions the same way that the gravitational constant functions, but we tend to write it as a combination of constants. We tend to write it as 1 over 4 times pi times this tiny number 8.85, which has crazy units. So notice we're putting a tiny number in the denominator of a fraction and putting those funny units in the denominator so that when it's in the denominator, if you do this on your calculator, if you literally did 4 times pi times this tiny number and then put the whole thing under 1, you would get 8.99 times 10 to the ninth newtons meters squared per second squared. So right now it's just like an inconvenience and a weird thing that I'm saying. So what I'm trying to say is the equation could be written like this. If you want to view it as perfectly analogous to gravity, you would write it like that, right? But actually, in context, it's more convenient ultimately to write it this way, where instead of writing a K, we write 1 over 4 pi epsilon naught. And epsilon naught is that tiny number, 8.85 times 10 to the 12, negative 12. I'll get to that, why that is. I just want you to know it before we lose sight of it. And the other thing with 2 minutes left, notice how well this works. After all my talk about negative and positive and all this, well, you know that with electricity, charges come in two varieties, positive or negative, right? So look at the equation now. You notice I didn't put a negative in front of it this time, nor did I put a positive. I don't have to put anything in front of it this time, but there is the R hat because notice if Q1 and Q2 are both positive, if they're both positive, then the whole equation will be positive. And what that would mean is that the direction of the force would be the same as the direction of the unit vector, the displacement vector. Like if both Q1 and Q2 are both positive, the whole thing will be positive. It won't have a negative sign on it. So we won't flip the vector. So the force will point from Q1 to Q2, i.e., it would be a push, which is exactly what protons do to other protons. They repel, right? Similarly, look how convenient this is. Similarly, if Q1 and Q2 are both negative, if they're both like electrons, a negative times a negative equals a positive. So the whole thing will be positive. So it'll still be a push, like you know from chemistry. But if the charges are opposite each other in any order, Then they'll make a negative sign come out, and then the thing will look like gravity. It'll have a negative sign in the front, and the displacement vector will be flipped. So then, and only then, it will be attraction. Do you see so gravity, there's always that negative sign. And masses are all positive. We put a negative sign there always because gravity is all attraction. This could be attraction or repulsion, and the sign of it, if it's positive, it's repulsion. If it's negative, it's attraction. And the sign of it is determined by the combination of the signs of the two charges, as you would have guessed from chemistry. So that's it for today. Congratulations again, really, really, really. And I'll see you Monday. I'm turning off the recording, but I'm here if there's any quick questions or anything.